Here are 10 pieces of gem trivia you can listen to in English. Now, let's get started. Gems from meteorite. Did you know that some gemstones were not formed deep within the earth, but by the violent impact of a meteorite? About 14.7 million years ago, a meteorite measuring approximately 1.5 kilometers in diameter crashed into what is now southern Germany. The impact, at a speed of over 72,000 kilometers per hour, generated immense heat and pressure that instantly vaporized the surrounding surface rock. This molten material was blasted high into the atmosphere, where it cooled and solidified into droplets of green natural glass, raining down primarily over the modern-day Czech Republic. These droplets are known as moldavite. Unlike diamonds or rubies, which can take millions of years to form under the Earth's crust, moldavite was created in a matter of seconds during this catastrophic celestial event. The site of the impact is now a 24-kilometer-wide crater known as the Rees crater. The unique wrinkled texture and tiny bubbles seen on the surface of moldavite are not flaws, but rather the preserved traces of its rapid, aerodynamic cooling as it fell back to Earth, making each piece a record of a cosmic collision. Diamonds from sea. When we picture diamond mining, we usually imagine deep tunnels far underground. However, some of the world's highest quality diamonds are found at the bottom of the ocean off the coast of Namibia, having been washed out to sea by ancient rivers. To retrieve these gems, mining companies undertake a truly massive engineering project. First, they construct enormous seawalls of sand, which can be several kilometers long and tens of meters high, to enclose a specific area of the coast. Then, they use powerful pumps to completely drain all the seawater from behind this barrier. This process exposes a section of the seabed that was once underwater. With the area dry, heavy machinery, such as bulldozers and excavators, can be sent in to dig up the diamond-rich layers of sand and gravel directly. This method reveals that diamond recovery is not confined to traditional underground mines. It is an extraordinary example of large-scale technology being used to alter the landscape, temporarily moving the ocean itself to access the treasures hidden beneath. Diamond weapon. Could diamonds have been the key to a space-based superweapon? In the 1980s, the United States Strategic Defense Initiative, a project nicknamed Star Wars, seriously investigated this possibility. The plan involved using high-energy lasers to shoot down enemy missiles from space. The main challenge was the immense heat generated by such powerful lasers. Researchers turned to diamonds because of their incredible thermal conductivity, which is approximately 2,200 watts per meter K, about 5 times that of copper. This property would allow a diamond lens to rapidly dissipate the intense heat, enabling the laser to be focused with almost no energy loss. However, the ambitious weapons project was eventually abandoned due to immense costs and technical difficulties. The research was not a complete loss. It spurred significant advancements in diamond synthesis techniques, particularly a method called chemical vapor deposition. While the space weapon was never built, these technologies are now essential in modern industries. For example, they are used in the production of highly effective heat sinks for semiconductors and in creating extremely durable industrial drills and medical scalpels. Diamond from peanut. Can you really make a diamond from something as common as peanut butter? Surprisingly, the answer is yes. A German geoscientist named Dan Frost successfully synthesized a diamond using this popular food spread. In his experiment, he replicated the extreme conditions found deep within the Earth's mantle. He placed a small amount of peanut butter between the tips of two tiny diamonds and subjected it to temperatures of about 1300 degrees Celsius and immense pressure. Under these conditions, the carbon atoms within the peanut butter rearranged themselves to form the crystal structure of a diamond. This experiment has led to a common misconception that peanut butter is a special ingredient for making cheap diamonds. However, the true purpose of the research was not to establish a new commercial production method. Instead, the scientists' goal was to simulate the geological processes that occurred deep inside our planet. Peanut butter was simply used as a convenient carbon source because of its chemical composition. In theory, any substance rich in carbon could be used to achieve the same result. Gem from space. Did you know that one of the most brilliant gemstones today was first found in a meteor crater? In 1893, the French chemist Henri Moissan discovered microscopic particles of what he initially thought was diamond in a crater in Arizona. It was not until years later that he identified the crystals as silicon carbide. This new mineral, named moissanite in his honor, has a hardness of 9.25 on the Mohs scale, which is very close to diamond's 10. Furthermore, its brilliance and fire, which refer to its sparkle and the breaking up of light into spectral colors, are known to exceed those of a diamond. However, naturally occurring moissanite is incredibly rare and almost never found in sizes large enough for jewelry. Therefore, virtually all moissanite sold today is created in laboratories. Scientists have perfected the process of synthesizing silicon carbide crystals, making it possible to produce large, flawless gemstones. This technological advancement has made a durable and dazzling gemstone accessible to a wider market, offering a popular alternative to traditional diamonds. Quartz Watch. Have you ever wondered why the quartz watch on your wrist is so incredibly accurate? The secret lies in a physical phenomenon called the piezoelectric effect. Certain materials, like quartz crystals, generate a small electric voltage when mechanical pressure is applied. Conversely, when an electric voltage is applied to them, they vibrate at a very precise and constant frequency. In a quartz watch, a battery sends electricity to a tiny fork-shaped quartz crystal, causing it to oscillate exactly 32,768 times per second. An integrated circuit then converts these steady vibrations into a single electrical pulse every second, which drives the watch's hands. Before the invention of quartz technology, watches were mechanical, powered by springs and gears. These timepieces were feats of craftsmanship, but were sensitive to external factors, such as temperature changes and physical shocks, which could affect their accuracy. Quartz crystals, however, are far less affected by these environmental conditions. This resilience is a key reason why quartz watches are not only more accurate, but also significantly more affordable and durable than their mechanical predecessors, revolutionizing the watchmaking industry. Sapphires at checkout. Have you ever noticed the small glass window on a supermarket barcode scanner? You might be surprised to learn it's often made from the same material as a precious gemstone. Many barcode scanner windows are made of synthetic sapphire glass. This is because of sapphire's exceptional hardness. On the Mohs scale, which measures scratch resistance, sapphire scores a 9, second only to diamond's 10. In a busy retail environment, thousands of items are dragged across the scanner window each day. Using a less durable material would result in scratches that could interfere with the laser and lead to inaccurate scans. Sapphire's ability to resist this constant abrasion ensures high transparency and scanning accuracy over a long period. While sapphire is ideal for this application, its widespread use in other areas, like smartphone screens, is limited by certain trade-offs. The main barriers are its high production cost and lower toughness compared to specialized hardened glasses. Manufacturing large, flawless sheets of sapphire is significantly more expensive than producing chemically strengthened glass like Gorilla Glass. Furthermore, while extremely scratch-resistant, sapphire is a crystal, making it more brittle and prone to shattering from a direct impact than some flexible modern glasses. Therefore, its use is often restricted to smaller components where extreme scratch resistance is the top priority. Colored diamonds. What gives rare green and blue diamonds their spectacular color? The answer isn't a chemical impurity, but rather exposure to natural radiation over millions of years. The color of many natural fancy-colored diamonds is the result of a physical process, not chemical composition. When a diamond forms near radioactive minerals in the Earth's crust, it is bombarded by high-energy particles. This radiation is powerful enough to knock carbon atoms out of their perfect crystal lattice structure, creating a vacancy or lattice defect. This defect alters how light passes through the diamond. It absorbs certain wavelengths of light and transmits others, which our eyes perceive as color. For instance, a specific type of defect known as the GR1 center is responsible for absorbing red light, resulting in a vibrant green appearance. This natural process has been replicated and refined by scientists to treat diamonds artificially. Colorless or less desirable diamonds can be exposed to controlled radiation in a laboratory using electron beams or neutron bombardment to create these color-producing lattice defects. Following irradiation, the diamonds are often heated in a process called annealing. This can move the vacancies within the crystal lattice, further modifying the light absorption and creating a range of other colors, such as yellow, pink, or blue. While these treated diamonds are visually stunning, they are generally less valuable than their naturally colored counterparts. Earth's gem factories. Have you ever wondered how precious gems like rubies and jade are formed? The answer lies deep within the Earth, where the immense forces of plate tectonics create what are essentially gem factories. At subduction zones, where one of Earth's tectonic plates slides beneath another, rocks from the surface are dragged dozens of kilometers underground. There, they are subjected to extreme conditions, including pressures over 20,000 times that at sea level and temperatures exceeding 600 degrees Celsius. This intense pressure and heat cause the atoms in common minerals to realign, transforming them into dense, beautiful crystals. However, not every tectonic collision results in a treasure trove of gems. The formation requires a precise recipe. Firstly, the original rock must contain the specific chemical elements needed for a particular gem. For example, aluminum and chromium for ruby. Secondly, even if gems are successfully created, they remain hidden deep within the Earth's crust. For them to reach the surface where we can find them, they must be carried upwards by millions of years of geological uplift and then exposed by erosion. This entire sequence of events is exceptionally rare. Ruby Revolution. Did you know that the laser, a tool central to countless modern technologies, was born from a gemstone? On May 16, 1960, physicist Theodore Maiman created the world's first functioning laser using a synthetic ruby crystal, about the size of a fingertip. He placed a powerful flash lamp around the ruby rod. When the lamp flashed, It excited the chromium atoms within the ruby, causing them to emit photons of light. These photons bounced between two mirrors, placed at either end of the rod, amplifying the light until it emerged from one end as a powerful, focused beam of red light with a wavelength of 694.3 nanometers. Despite its scientific success, the invention was not an immediate hit. At the time, many in the scientific community dismissed it as a solution looking for a problem, viewing it as little more than a scientific curiosity with no practical applications. This perception, however, was short-lived. Over the following decades, the principles behind Maimon's ruby laser were developed to create technologies ranging from barcode scanners and DVD players to surgical tools and fiber optic communication, fundamentally reshaping our world.